Hello, and this will be the last of the topics that we do before the summer holidays. Well done on completing year one. So we're going to look at the reverse chain rule for integration, and this builds on what we looked at last time when we looked at our standard results. And we've got two very specific cases to look at. So without any further ado, let's just get into it. So the first instance is where we're integrating a function which appears to us as a fraction. And whenever I'm integrating a function that appears as a fraction, I'm looking for one thing, and I want you to be looking for the same thing. I'm looking at the denominator, and I'm thinking, if I differentiate the denominator, do I get something that looks like the numerator? And by that I mean, in this example, if we differentiate x squared, do we get something that looks a bit like 2x? Now, in fact, we actually do get exactly 2x. Now, when this happens, we are using an instance of the reverse chain rule. Okay, so we're just considering the chain rule and working it backwards, because the reverse chain rule will work for functions that are fractions that follow this pattern, where we have k f dash x divided by f of x. As you can see, if you differentiate the denominator, do you get some multiple k of the numerator? And that then elevates what we're able to do. We've been integrating fractions so far where we have a number as the numerator, but up to this point, nothing that's a function of x as a numerator. Now, you might be asking yourself, well, what if you differentiate the denominator and you don't get the numerator? Well, then we have other methods that we will learn later in the course that we have to integrate those. But for now, we're going to be looking at examples where we can. So to get into this example here, if we're integrating 2x over x squared plus 1, like I said, the first thing I'm looking for is, if I differentiate the denominator, do I get a multiple of the numerator? And I do, okay? And in this case, when we have this fraction relationship, then we try natural log, okay? Just like we did when we had something over x, we try natural log. That's our go-to. So when we have this fraction, think about natural log of f of x. So let's use our guess differentiator just and see how we get on. So the guess is going to be natural log of x squared plus 1, okay? When we have a fraction, natural log, because that's what happens with fractions. There are exceptions to that. For example, when you have a denominator where the whole denominator is raised to a power, no natural logs, all right? But in this case, we'll try natural log. We differentiate our guess, and we have 1 over x squared plus 1. Then we have to differentiate the x squared plus 1 to get 2x, and we multiply together, which ends up with 2x over x squared plus 1. Now, this is exactly like we did with standard results, except, obviously, when we differentiate this function, we actually get a function of x. Okay. Now, then we make any adjustments, and we can see that 2x over x squared plus 1 is exactly what we were after in the first place, so there are no adjustments in this case. So our integral is just natural log x squared plus 1, and not forgetting our plus c on the. So the second example, we have the integral of cos x over 3 plus 2 sine x. And again, thinking this process through, if I was approaching this integral, I'm looking at this fraction and I'm asking myself, can I differentiate the denominator and come out with something like the numerator? And yes, if I differentiate 3 plus 2 sine x, then I will get 2 cos x. So it follows this rule. And so therefore, I'm going to guess, and again with fractions, if it follows that rule, natural log is our guess. So I'm going to go with natural log of 3 plus 2 sine x. If I differentiate 3 plus 2 sine x, natural log 3 plus 2 sine x, then I'm going to get 1 over 3 plus 2 sine x. Okay, that's that differentiation rule for natural log. multiplied by what we get when we differentiate the 3 plus 2 sine x using the chain rule. So differentiating 3 plus 2 sine x, we get 2 cos x. So this becomes 2 cos x over 3 plus 2 sine x. And then we compare that with what we wanted. And I can see that I've got 2 cos x instead of 1 cos x. So I go back to my guess and I adjust by dividing by 2. So therefore my integral becomes 1/2 natural log 3 plus 2 sine x plus c. Not forgetting the modulus sigma. Now that's it for the first instance of reversing the chain rule. The questions I'm going to set you, I want you to pause the video here, stop the video. I want you to access the first set of questions, and I want you to practice that skill. Every single question that you can see, these are the questions that you'll be set. Every single question, I mean, I'm giving you the clue right here, it falls into that rule. All right, you can see from this one, if you differentiate x to the 4 plus 2, you're going to get a multiple of x cubed. If you differentiate 1 plus cot x, you're going to get a multiple of cos x squared x. So stop the video, work on the questions, and then come back and watch the second. So welcome back to the second half. The second instance where we're looking at reversing the chain rule is when we have this situation. Now what we do here, if we look at these functions, and it's perhaps easier to see in the second function, if we have this function of x squared plus 5 raised to the power of 3, i.e. we have f of x all raised to a power, let me just pop that in a pair of brackets so you can see what I mean. If we have this whole f of x raised to a power, and it's being multiplied by a multiple of the derivative of this f of x, then we can apply another instance of the chain rule. So looking here, x squared plus 5, the bit in brackets, ignoring the power of 3 for now, if I differentiate x squared plus 5, do I get some multiple of this x? Yes, I do. I get 2x. Looking back to this one, if we look at this sine squared x, and again, we're always looking at the function that's being raised to the power, okay? We looked at x squared plus 5 to the power of 3. Here, we're looking at sine raised to the power of 2. So if I differentiate sine squared x, do I get some multiple of cos x? And the answer is yes, I do. So when we have this, what we have to try is the function of x all raised to the power of n plus 1. That's our guess. So we add 1 to the power, and then we make an adjustment. So for part A, we have 3 cos x sine squared x dx. If we differentiate the function with the power, the sine squared, do we get a multiple of the cos? Yes, we do, because sine differentiates the cos. So my guess, this is all I'm not expecting you to jump straight to the answer from this, but just what is your educated guess? Your educated guess is going to be sine cubed x, i.e. raise the power of that by 1. When we differentiate sine cubed x, we get 3 sine squared x, and then we have to remember to multiply by the derivative of sine x in our answer. Okay, now that's going back to the chain rule, and I haven't explained it as explicitly as I did in the chain rule video because I'm hoping we're at that point now where we can see this. The 3 comes down, drops down to a 2, we differentiate sine and get cos, and we multiply the 2 together. So we have 3 sine squared x cos x. And then we make any adjustment that we need to make. Now actually, if we look, 3 sine squared x cos x is the same as 3 cos x sine squared x. So there is, again, in this instance, no adjustment to be made. So we can say that this integrates to sine cubed x plus c. So following this rule through then, for the second example, we have x multiplied by x squared plus 5 to the power of 3. what I'm looking for when I have this product of two functions of x is one of them raised to a power? Yes, it is. X squared plus 5 is raised to a power. If I differentiate the one being raised to a power, do I get a multiple of the other one? Yes, I do. I'm going to get 2x, but I want x. So I can already see what's going to happen here. I can already see how I'm going to make an adjustment. So my guess is just going to be x squared plus 5 to the power of 4. Okay, take this whole function here and up the power by 1, exactly like we did with our standard results. We differentiate this guess, we get 4x squared plus 5 to the power of 3. And then because we have to differentiate using the chain rule, we multiply by the derivative of what's inside the bracket, which is 2x. And that becomes 8x, x squared plus 5 to the power of 3. Did we get something similar? Yes, we got something similar. How far away are we? We're out by a factor of 8. Our answer is 8 times too big. And so we divide our initial guess by 8. So that means that our integral for x times x squared plus 5 to the power of 3 is 1/8 of x squared plus 5 to the power of 4 plus c. And we're done. So the next set of questions is practicing that particular iteration of the reverse chain rule. And then we'll have another lesson or two, depending on how quickly we've gotten through this, where we will practice all of those skills before you go on your summer break. All right. Have a go at the questions. Here they are. You can see they all fit that pattern. There are the answers. And the question, I'll put these as a PDF in the lesson plans area that you can get access to as well. All right. Thank you very much.